Okay, it's 1 o'clock. Welcome everybody to our clinic, and let's get started. There are lots of material to cover. Let's start with our questions. This is just a question that I keep carrying on. I don't have an answer to that, but Marta submitted a question. She's interested in PyDarshan and the analysis of HDF5 Darshan logs, and she has a resource here, which is one of the Jupyter notebooks, which I believe my colleague Alexander put together once. And let's see, any other reference or documentation that you could point to? Okay, maybe just to clarify the question a little bit for everyone here who may not have used Darshan. So Darshan is definitely a great profiling tool, and for profiling I/O, and not just HDF5 I/O, POSIX I/O, MPI I/O, and so forth. And what Darshan does is it gives you these files that contain these things called performance counters, and they are broken out by the runtime, be it POSIX I/O or standard I/O or MPI I/O or HDF5 in some cases, and they're broken out by file, and it's great diagnostic information. And so yeah, it's definitely a great tool to use that tells you a lot about what kind of I/O your application is doing. Now, when it comes to interpreting these counters, sort of my go-to place, and of course, so PyDarshan, the default Darshan situation is you either link your application against the Darshan library, or you can also LD preload the Darshan library at runtime without making any modifications to your code or even relinking. And that will create a Darshan output file. And yeah, then there is a C API to inspect or introspect into these counters. And but then recently, I think in the 3.0 or 3.1 release, the Darshan guys introduced a Python module that lets you look at these Darshan counters, and that was a great step in the right direction, because people, I think, are more likely to write Python scripts to inspect that information rather than writing C programs, because it's just a lot of boilerplate and other unnecessary code that you have to write in C, whereas if you can write a Python script, that's much more convenient. Now, but the question is about the analysis. Yeah, so Alexander's sample Jupyter notebook here doesn't really, it really just shows you how to use the API, what's in there. And then here, for example, lists the types of performance counters that you can get. So for example, this would be a performance counter where H5D read operations that have occurred where the read request size was between 1 and 10 kilobytes. And then so there would be a counter here that tells you that there were 1,000 of these, or in some cases there were 0. So and then with counters like this, then the question is, well, what do they tell me about my application, or should I be concerned? I think that's maybe the more interesting question. And the answer is, well, it takes some time, and it helps to first maybe look at the counters from something where you think you know exactly what's going on. So for example, let's take a benchmark like IOR, where you can dictate and you can say, okay, I want to write 1 gigabyte in 4 megabyte blocks, and then read it back. Then you can kind of in your head predict, or with paper and pencil, predict what the Darshan counters for this should look like. So for example, I just said, I forgot already what I said, but let's assume I write 1 gigabyte in 1 megabyte blocks and then read it back. Well, and let's assume I use HDF5 rather than POSIX. I mean, this is for H5D read, but there are similar performance counters for POSIX, but let's assume we are doing that using HDF5. So if the block size is between 1 and 4 megabytes, I would expect on the read side, for example, to see 1 gigabyte divided by 1 megabyte. That should be the value of that counter here. And likewise, for the write operations down here, I would expect the H5 size write aggregate 1 to 4 megabyte. I would expect that to be exactly 1 gigabyte divided by 1 megabyte. And so that kind of gives you, once you've done that, you have sort of an idea, you can articulate an expectation of, based on what you know, what's going on in your application. You can say, well, I think my application is doing this, it's writing those attributes, it's writing those data sets, it's reading this and reading that, and then you can sort of have an intuition about what you expect to see in these counters. And then it's of course interesting to see how closely your expectation matches what's going on in reality. And that's where it then helps, for example, to look at, you can plot these histograms, for example, and maybe this is not a particularly interesting case here, but let's just take that example. So in this case, we are doing POSIX IO rather than HDF5 IO, and we see that we have a pretty large number of reads in this case. Reads is blue, writes is orange, between 1 kilobyte and 10 kilobytes. So this is just like a logarithmic range, if you wish, down here, not exactly, but so of course there were only, I don't know where this 400,000 comes from, but if I take this as a 4, that would just mean there were 4 reads or writes. If this were a scaled thing, so if this were, what is this, 40 million or 400 million, if these were 400 million 1K to 10K reads and or writes, I would be concerned, because unless you're writing to a local SSD, a parallel file system, for example, is not going to perform very well if you do 400 million 1K to 10K reads and writes. That performance cannot be good. So performance cannot be good in the sense that if you say the vendor tells me that this parallel file system is capable of doing X gigabytes per second or something like that, well, with a workload like that, you're not going to be near that number that the vendor will give you. So and sort of this comes to the question of, well, how to interpret these numbers. And there is actually some documentation. So if you just go to the Darshan documentation page itself, there is a section here on analyzing log files that goes a little bit through the mechanics, but then explains what these counters mean. And I think then it just takes a little bit of experience in the sense of an intuition of how do parallel file systems work, that there is sort of a metadata component, a metadata server to that, a data server to that, how I/O happens, what kind of I/O optimization techniques there are, like aggregation, that there is, if you're dealing with MPI, there's something called independent and collective I/O and things like that. But fundamentally, small I/Os, especially with parallel file systems, are problematic, meaning small compared, let's say, to the block size or to the stripe size of the parallel file system. Let's say in the case of Lustre or GPFS or OrangeFS, you typically have a stripe size. And so yeah, small I/O, 4 kilobytes, 10 kilobytes, that's all. If you have a lot of those, that's definitely a warning sign or something to be concerned about. But beyond that, it's really, yeah, live and learn, more or less. And then, of course, there are some timing statistics here. In the case of parallel job, the fastest and the slowest rank. And if there is a lot of variance between a large spread between the sort of fastest and slowest performer, those are things to look for. But I don't have, I don't know if Marta is here, but I don't have anything magic to say or to say that this is easy, or it just takes experience. So you just have to try. And if you have a specific question, then you can certainly always post something on the forum, or talk to the help desk, or I don't know. Does that answer the question a little?
Yes. Hi, this is Marta. I'm here. Thank you. Thank you for at least replying to the question. I know that I posted a little closer to the presentation. So eventually what I'm trying to understand is, so which box will be over each one? Because right now we have POSIX and we have also MPI-IO, but so it will be HDF file containing those, or I'm trying to understand that more.
Yes. Good question. For the HDF5 side, so Darshan has these different performance counters, and of course you can do IO with HDF5 on top of POSIX, but you can also do IO with HDF5 on top of MPI-IO. And which of the two applies for your particular application, only you can know, because you know when you set the file access property list, the set FAPL, if you specify set FAPL MPI-IO, then that means you will be using HDF5 on top of MPI-IO. And yes, there might be some POSIX or some standard IO because you are printing messages to a console, to a terminal window or something. That will cause some standard IO or POSIX IO you're writing to a pipe or something like that. But HDF5 will be running on top of MPI-IO, for example. So you have to know that based on your application. And that would then be included. So you would, in a way, get two perspectives on the same information. Now, of course, this can be arbitrarily complicated because in the same application, you can do HDF5 IO on MPI IO in some parts of your code, and you can do also HDF5 IO on top of POSIX in other parts of your code. That there's no limitation from the HDF5. So I'm not saying this is a good idea or I recommend it, but it's possible and maybe sometimes necessary. But then, so if you are interested just in HDF5, you can just look at the HDF5 performance counters with the understanding that some, if there is some POSIX and some MPI-IO, that will be included twice, so to speak, depending on what HDF5 uses in terms of its file driver.
Yes, I guess. Yes. I think, yeah, you describe pretty well probably what I'm gonna see if I use this tool. That is the main. Yeah, I guess I have to dig in more in how the current IO is done, but I wanted to, from your point of view, at least, do you think it's useful to try to understand?
Oh, definitely. And if I were you, again, I would use initially just something like IOR, where the IOR benchmark, and I can include the link in the notes if you want. With the IOR benchmark, you can actually control which IO runtime to use. So you can run IOR with POSIX, you can run IOR with MPI-IO, and you can run IOR with HDF5. And then if you just run the same benchmark, meaning write 1 gigabyte in 1 megabyte blocks, you can sort of look at the 3 different Darshan files and compare them. And then you would see, in the case of HDF5, that yes, that there would be most likely, assuming you do this in parallel, an MPI-IO, there would be non-zero MPI-IO performance counters. but then there would also be non-zero matching HDF5 IO counters.
Yeah, that will be very useful. Thank you.
Yeah.
So you have the link.
Yeah, I'll add it to the notes. It's basically IOR. I'll include it in the notes later. I can't edit that file right now. There are others, IOR or FIO. I think, yeah, those are an MD test is also a good one. So I can, for now, just post it here in the chat, but I'll add it to the notes after that meeting. Okay.
Thank you so much.
Okay, great. Good. Well, that's why we are here. Let's just see what was happening, unless there is another question. I'm going to pause here. Are there any other questions out there? No? Okay. Last week's highlight, HDFU 3.13 was released. Here's the link to the forum post, which has the link to the downloads and so forth. There were a few interesting questions that caught my eye on the forum. Number one, yeah, someone was asking about the problem they had was a colleague or they themselves were reading from a data set of a compound data type, meaning there were fields of a certain type and potentially nested and so forth. And unfortunately, that person or a colleague had misspelled the name of one of the components. And the behavior of the library in this case is because we support what we call partial IO, where you specify the field names that you want to read or write. And if that's a subset of the fields in the file, then only those fields that match will be read or written. Everything else will be ignored. Unfortunately, in this case, for this person, there was a typo in one of the field names, and that means when you read it, there's just going to be garbage or fill value in that field. And then, so the question of the person, I believe, was how can this be avoided or prevented? And the answer is it's not as straightforward as we would like it to be. The main reason being that what is an error in this case is really, as I would say, in the eye of the beholder, or it really depends on what's, in this case, for some people would be an error, would be the correct behavior for other people. So you're kind of caught in the middle here. And what I could see is if you want to read all fields of the compound type, you could use, there's a function called h5t equal that accepts two data type handles. And this function will tell you if the handles that those two the data types that are referenced, if they are the same type or different types. Now, there are some caveats here. Number one is two compound types will be equal only if they have the fields have the same names, and I believe they have to be in the same order. So if the second compound type, let's say, has the same fields but in a different order, h5t equal would not recognize them as equal, so it would say they are not equal. Another thing is that, of course, the types of these fields have to be identical too, and they also have to be identical in the sense that if there is a valid type conversion between the two, that's not good enough. So let's say in one case you have a 32-bit integer in little endian, in the other case you have a 32-bit integer in big endian. Again, h5t equal is not going to accept that. They have to really be identical, not just equal in an abstract sense, they have to be identical. And the way to accomplish that would be when you have the in-memory data type, and then you can read with an h5d get type the data type from the file, and then there's a function called h5t get native type that will convert this data type into its in-memory form, and then you can do an h5t equal on those two. And then I think H5T equal says in that case they are equal, you can be pretty certain, that you are not going to be plagued by this issue that somebody maybe misspelled a component name or something like that. But then, of course, if you're not interested in reading all fields, then it gets trickier, and unfortunately H5T equal is not going to help you there. It's going to help you if you can create sort of a reduced, meaning with fewer components, fewer fields in memory type, and a reduced with fewer components in the file type, and then use the same trick, but it's more work on your part. Other than that, I would say the only other way is to really, obviously a typo is something, is a user error if you wish, and if you can help it, do not allow your users to specify that symbolic information by typing. I mean, there should be, if it's in a GUI application, it really depends on the application. There should be only predefined choices that you are confident are correct to prevent something like that. And then, of course, last but not least, I think we talked about that in the previous to last clinic where someone asked about the use of named data types. Yeah, the use of named data types, if you have a compound type, you can save that data type definition in the file as an object. And then also when you create a data set or an attribute, you can use that type definition in the creation of these data sets and attributes. And that sort of makes it harder to introduce errors like that. But unfortunately, yeah, there is no perfect way, and this is really sort of one of the maybe more tricky bits. There was another question about using parallel HDF5 with compression, and a user noticed two things. Number one, the combination where you were using compression, but on top of that, a data transformation. And the data transformation is very simple. You can define a symbolic expression that basically supports the 4 primitive arithmetic operations, and it's only supported for integers and floating point types, so multiplication, addition, division, and subtraction. And what he noticed is that in sequential, there was no problem with working with compression and the data transformation, however, not in parallel. And I think, and he was asking if that was a design, if that was a bug or a feature. I think the answer in this case is there's fundamentally, since the data transformation is not going to change the size of the data set element, in theory, I don't see that particularly difficult. It's just another stage in the processing pipeline of the chunk, but my suspicion is that that was just dropped in a rush, so to speak, when that parallel compression was implemented first, and then nobody went back and revisited that. So, but I think fundamentally, I don't see anything why that couldn't be supported. And then there is a mentioning of the collective requirements. So when you do this compression in parallel and you apply it when writing a data set, there is a requirement for that to be collective. And that's actually mentioned in the 1.10.2 release notes. But again, who reads release notes, number one, and number two, there should be a more prominent spot to remind people of that that's a requirement. And for myself, I will take that as an action item to just add a note for all H5P set deflate, H5P set SZIP and whatnot, a note that basically says, hey, if you are planning on using this in parallel, then be aware that currently data transformations are not supported, and your rights have to be collective. Okay, those were the two that stood out for me. I mean, there was build issues and other things, but nothing really that caught my eye. Unless there's another question, I'll pause here, but then I have a little bit of a tips and tricks prepared. So are there any other questions so far? No? Okay. For today's tips and tricks, I prepared a little example of, this is a function that's actually in the develop branch right now. So I forgot if it's going to be released with 1.12.2 or 1.10.8 or 9. But it's there and you can actually use it, and it doesn't really have anything to do with file format and so forth. It's just a convenience API. The function is called H5D chunk iter, and as the name suggests, it has something to do with chunk data sets, and in particular, you can iterate over the chunks in a chunk data set and basically retrieve information about these chunks, how big they are in the sense of physical allocation, what kind of filters are, if any, are applied to them, and so forth. And so where this feature is kind of handy is, for example, let's say you are using compression with your data set and you would just like to know, well, how good is the compression ratio, although you could run H5 dump on that and that would give you some information. But then if you want to see, well, is the compression working equally well on average across all chunks, or are there some chunks where the compression is actually not working so well, and then some chunks where it's actually working extremely well, which is typically what happens, because depending on the physics or whatever you are, the data, where the data stems from, the effectiveness of these compression methods can be all over the place. Again, it's in develop right now, but to illustrate that, let's write a simple chunk analyzer, how you would use that function. And the code is in the GitHub repo, in the notes and so forth, and it's actually repeated here. So I'll quickly go through it, but I invite you to sort of explore it on your own time and run it. Again, you need develop. So the idea is basically a main function that takes one argument, the name of the file that you want to look at. And what we will do is we will basically iterate over all objects in that file. Of course, we are interested only in chunk data sets, but to get started, we will just be visiting all the objects in that file. And then we need to provide a callback function that I call the visit callback function that we will invoke every time we encounter an object. So that callback will look like this. This is our visit callback function. Well, first of all, we are looking at data sets only, so we are not interested in groups or named data types. And then if we have a data set, again, since we want to do chunk iteration, we have to look at the layout of that data set. So we have to retrieve the creation property list of a data set and check if it's chunked. And hey, if it's chunked, then we are good to go. So if it's chunked, we basically want to find out, well, what is the data type of the elements in that data set. Then we would like to find out what is the rank of that data set, the number of dimensions. And we would like to find out how large a chunk is nominally. So since we are, if we are applying compression, then the physical size of the chunks, of course, will be different from that nominal size. But if there's no compression, then we can calculate the size of a chunk based on the dimensions, the rank, and the size of an individual element. And that's what we are doing here. So, and then we are just printing that information. We are saying, hey, at this path, there is a chunk data set, and the nominal chunk size is this. And then we call our new friend, H5D chunk iter, which basically takes a data set handle, the data set transfer property list, which we are not using, and then basically another callback function that gets invoked for each chunk. And at this point, we are only interested in the size of the chunk. And if you look at the prototype of this chunk callback, you're basically getting the logical offset of the chunk in the data set. You're getting the filter mask, so you could look at compression and things like that. You get the physical address of that chunk in the file, and you get the size in bytes of that. And that's what we are printing. Plus there is some user context which we are not using in this case. So if you wanted to, for example, gather some statistics about that on the side, you could pass that in as this context argument. So if I do this, and I want to show you that in action, so you can compile this, and then I have an HDF5 file here, and let me pipe this through less. So it's going to print the path to that data set. The nominal chunk size here is, for example, 800 kilobytes, let's say, roughly. But these are the real sizes. So here we are iterating over the chunks, and you are seeing there is some variability here. And likewise for other data sets. The variability is not tremendous, but again, it could be depending on what this data set, what the data in this data set represents, could be very different. And yeah, that's pretty much it. I think also time is up. So yeah, please look at that code in detail, ask a question if that wasn't clear. And thanks for coming, and I'll see you next week. Thank you.
You have a question on the chat.
Oh, I have a question in the chat. I apologize. Let's see, where can I see the chat? Here, okay. Okay, I'm relatively new. We capture frames of RGB data from image devices, save each frame as a data. We get approximately 150 giga and save each frame as a data set in a group is about 6. Well, would chunking be benefit? So generally speaking, I think unless you have a good reason to, creating a separate data set for each of these frames may not be a good idea. I mean, if your frame rate is 1 per second, and that's maybe okay, but if you are acquiring tens of thousands, hundreds of thousands of frames per second, then that's not going to fly with creating a separate data set for each frame. So I would create, and then you have to think about, I don't know if the resolution of your images is constant or if it varies over time. But the images of the same resolution, you want to stack them together in a 3-dimensional data set. And then, yes, in this case, you can think about chunking because you want typically blocks of or stacks of images in one chunk. And then the question, however, would be when you apply compression, what kind of compression algorithm works well? So if you have more sort of a differential, meaning if your images, there's something going on in some parts of the image, and since we have that third time dimension then, and we have a chunk, a 3-dimensional chunk, compression may actually work very well. However, it will not be as good as sort of more image optimal, like an MPEG compression, for example, where you can do very clever incremental compression. Then you're not going to be quite as good, but you will get pretty decent results. And so there are lots of questions. So what we can do is from Daniel Williams, Daniel, you can either post a question on the forum, or you can send me an email. I mean, I'll put my email address here. You can just send me an email, and we can continue that conversation, because yeah, we are out of time, unfortunately. Okay, is that good? Okay, I guess that's it for today. Okay, I'll see you next week. Yeah, okay, I'll see your email. Bye.